Next technique of integration is what I refer to as my trigonometric substitutions. Now, if in the integrand's position you have an expression of this form, that is to say, the difference of two squares, the appropriate substitution I'm going to commit to is this one. Now, I'll illustrate why this works so nicely in my first example. Now, you're used to doing something very different from this. You're used to making up a substitution in which is the new variable that's equal to some expression in the variable integration. Here, it's a very backwards type substitution. I will let the variable I already have in the integrand's position to be this, my a, times the sine of my new variable theta. Now, paying the consequence of my actions, here is the relationship between dx and d theta. Next, in committing to the substitution, let's see, symbol by symbol, my numerator does not change. Here is my new denominator. Now, here's the tricky part. You take a peek at the radical factor downstairs. Committing to my substitution, doesn't it look like this? Continuing. Now, I am experiencing that ancient problem of lack of board space. So if you don't mind, number one, 2 gets factored out of these two terms in the radicand's position. Next, the square root of this product is a product of 2 square roots. Next, these 2 factors cancel. And if you don't mind, I'll pull out my 4. Now, would you not agree that this binomial expression via my first Pythagorean identity is equivalent to this? And because we are 9th grade algebra experts, would you agree that the square root of that square is not that? It's really this. That's a problem. However, keep in mind that it was a backwards type substitution. The new variable theta is described in terms of the inverse sine of x over root 2. Because theta is the inverse sine of something, it's an angle that lives between negative pi halves and positive pi halves. That means it's an angle that lives in the 4th quadrant or 1st quadrant. But any angle whose terminal side is in the 4th or 1st quadrant in scalar position has a positive cosine value. It gets me out of this trap of having absolute values in the integrand's position. Oh, by the way, that was raised to the 4th, wasn't it? My apologies. Continuing to save myself some room. These 2 cancel. So I have this. My technique for evaluating trigonometric integrals involving trigonometric expressions is the same for cosecant and cotangent as is for secants and tangents. So, you know where I'm going to go next. I will shade off 2 factors of the cosecant of theta. What's left over is cosecant squared, which I can now rewrite as this. And of course, committing to a z substitution. Look at that. It's merely a quadratic expression in the integrand's position. That makes life so easy. Now back substituting. Trying to write my final answer in terms of x. Notice what this original substitution truly tells me in terms of a relationship between these two. So does he really say this? Now, if I were to embed theta into a right triangle as one of its acute angles, to say that its sine is its fraction simply means the ratio of the vertical leg to the length hypotenuse is this ratio. Using my Pythagorean theorem, I have the length of the other side as an expression in x. Notice how you saw that somewhere in the original integram. So let's finally answer a question. Actually, can I take that back? Instead of answering my question, can I clean it up a little bit by pulling out this 1/3? It just looks nicer. Now, the cotangent of theta is this over this. Again here. And if you really want to make that look pretty, don't think I can do anything better than that to clean it up.